Hello, my dear students. I hope you all are doing great. Dear friends, today we'll be talking about alcohols, phenols, and ethers. Let us start with the alcohols first. First of all, you must know that what are alcohols. So let's have a look at the definition of alcohols. Remember always, my dear friends, alcohols are the hydroxy derivatives of aliphatic hydrocarbons. And remember always, this aliphatic hydrocarbon basically means open chain hydrocarbons, my dear friends. This aliphatic term means open chain hydrocarbon. Open chain hydrocarbon. So I told you that alcohols are the hydroxy derivatives of aliphatic hydrocarbons, my dear friends, and the alcohols are represented by ROH. The general formula will be CnH2n plus 1 OH, my dear friends. Remember this particular point. Let's move further. Now, my dear friends, if you look here, you can have now aliphatic and aromatic alcohol. So let's make a difference between the two. If you talk of aliphatic alcohol and you talk of aromatic alcohol, my dear friends. So what is the difference between the two? How can you distinguish between the two? So very simple it is. Let's take an example of, first of all, aliphatic alcohol. And you are aware about the fact aliphatic means open chain, my dear friends. So obviously, here the OH group will be attached to the aliphatic carbon chain. So look here, OH group is attached to, so I will write down, OH group is attached, or you can say linked to aliphatic carbon chain. Carbon chain. Now look at aromatic alcohol, my dear friends. What is aromatic alcohol? Very simple. Look here, I will take on a benzene ring, okay? Then I will take a side chain here, CH2, CH2, and OH. And look here, if you look at the alcohol at this point, alcohol is attached to, my dear friends, again to a side chain. This is the side chain. So I will call it as side chain. And it's a side chain on aromatic hydrocarbon. Benzene is aromatic hydrocarbon. So your benzene is aromatic hydrocarbon. So dear friends, now if you look here, how can you define now aromatic alcohol? It's a very simple thing, my dear friends. It is actually the hydroxy group or hydroxyl group present in the side chain of an aromatic hydrocarbon. So aromatic alcohol means, my dear friends, aromatic alcohol means OH group present in side chain of aromatic hydrocarbon. Side chain of aromatic hydrocarbon. Very simple thing it is. Let's take an example, my dear friends here. We will take one or two examples and you will understand it. This is our aromatic hydrocarbon, benzene. And let's take one side chain. This is the side chain of aromatic hydrocarbon and attach OH group. And this will become your aromatic alcohol. Let's take on one more example. Let's take on aromatic hydrocarbon. Benzene is aromatic hydrocarbon. So this guy is your aromatic hydrocarbon, my dear friends. Let's take one side chain here. So have a look, my dear friends, and this will become your aromatic alcohol, my dear friends. Let's take one more example. Let's take aromatic hydrocarbon, which is benzene, and let us attach CH3 groups and OH. And this guy will become your aromatic alcohol. I hope you have understood this thing. Let's go further. Dear friends, now we can classify the alcohols on the basis of number of OH groups present in their structures. So how many OH groups are present in an alcohol? We can classify them into monohydric alcohol, dihydric alcohol, trihydric alcohol, or you can also call it as polyhydric alcohol. Polyhydric alcohol. So how many OH groups are present in an alcohol? We can classify them on the basis of that into monohydric, dihydric, and trihydric, my dear friends. So let's take an example here. If you talk about this simple thing, CH3, CH2OH, this alcohol is my aliphatic alcohol that I know, and it contains only one OH group. So when it contains only one OH group, then you should understand that it is a monohydric alcohol. It's a monohydric alcohol. So now look here, my dear friends, CH2, CH2, OH, OH. This is also my aliphatic alcohol, but it contains two OH groups, my dear friends. So when it contains two OH groups, then you should tell that it's a dihydric alcohol. Dihydric alcohol. And we call it as glycol. And the first one is known as ethanol. That is the name of that. So let's go further, my dear friends. Let's take on one more alcohol here. Have a look here. It's very simple. Here we have three OH groups. So I can call it as trihydric alcohol, or you can also call it as polyhydric alcohol. And the name of this molecule is glycerol, my dear friends. So this is glycerol. So first one is ethanol, which is monohydric. Then here we have two OH groups, so it's dihydric. And here we have three OH groups, so it is trihydric alcohol, my dear friends. If you take one more example, let us suppose if we take on CH2OH, then you take on CHOH, again CHOH, again we'll take on CHOH, then we will take on CHOH, and finally we will take on CH2OH. This can be also written as CH2OH, then we can write on CHOH 4 times, then CH2OH. Now this kind of compound is called as alditol, and this alditol contains almost 4, 5, and 6 OH groups. So you can also call it as hexahydric alcohol, or you can directly call it as polyhydric alcohol. Polyhydric alcohol. I hope, my dear friends, you have understood this important term. Let's look into classification of alcohols based on attachment of OH group to sp3 hybridized carbon, which means that OH group should be attached to sp3 carbon. So let's have a look. We have three types here: normal alcohols, allylic alcohol, and benzylic alcohol. Let's take on the first one. So here obviously OH group has to be attached to the sp3 carbon. So this is our sp3 carbon, my dear friends. So let me mention here, we have sp3 carbon here, and OH group is attached to sp3 carbon. This is our normal alcohol. So let's go for the allylic alcohol. In allylic alcohol, we have OH group attached to sp3 carbon, correct? But that sp3 carbon is next to carbon-carbon double bond. So that is the important point here. So dear friends, in allylic alcohol, you have OH group attached to sp3 carbon, just like normal alcohol. But here is a little difference, that this sp3 carbon is next to carbon-carbon double bond. So this sp3 carbon is next to carbon-carbon double bond on which OH group is attached. So it's an allylic alcohol. Let us go for benzylic alcohol, my dear friends. In benzylic alcohol, you need basically a benzene first. Then after that, you need a CH2 group. On that CH2 group, you have OH. My dear friends, this CH2 group means the carbon will be sp3 hybridized. So here OH group is again present on sp3 carbon, because our classification is based on attachment of OH group to sp3 hybridized carbon. So obviously, but that sp3 carbon is next to benzene ring. So when sp3 carbon contains OH group is next to the benzene ring, we call it as benzylic alcohol. When sp3 carbon is attached to OH group and that sp3 carbon is next to carbon-carbon double bond, we call it as allylic alcohol. And when OH group is present on sp3 carbon, that is just a normal alcohol, my dear friends. And we can further, my dear friends, classify them into primary, secondary, and tertiary, or we can also call them as 1 degree, 2 degree, and 3 degree. So let us take a normal alcohol first. Now you are aware about a normal alcohol, its structure. So structure of normal alcohol, everybody is aware now. It will be your R, CH2, OH. So OH group is present on sp3 carbon right out here. So it can be 1 degree, 2 degree, and 3 degree. So let's have a look. It's a very easy thing. Let's try to understand. So normal alcohol can be your 1 degree alcohol. It can be your 2 degree alcohol, or you can be at 3 degree alcohol. So let's have a look. What is 1 degree alcohol? Very simple it is. Let us see here we have CH3, CH2, OH. Now look at this carbon. This carbon is called as 1 degree carbon because it's attached to only one other carbon directly. So it's a 1 degree carbon. So this alcohol will be called as 1 degree alcohol or primary alcohol. You can call it as 1 degree alcohol, or you can also call it as primary alcohol. Now look at the 2 degree alcohol, my dear friends, where the OH group will be present on 2 degree carbon. So look here, my dear friends, if you have CH3, C, CH3H, and OH. Now OH group is present on attached or to sp3 carbon, but that sp3 carbon is here 2 degree carbon, my dear friends. So this sp3 carbon is here 2 degree carbon. So I will mention it. sp3 carbon as 2 degree carbon because it's attached to 2 carbon atoms directly here. So it's a 2 degree carbon. So alcohol will be 2 degree alcohol, or you can also call it as secondary alcohol. After that, my dear friends, let us take on now tertiary alcohol. For tertiary alcohol, I need tertiary carbon. So have a look here. Look at this carbon. This is your tertiary carbon because it's attached to 3 carbons directly, 1, 2, and 3 carbons directly. So this is tertiary carbon, and OH group is present on it. So it is called as 3 degree alcohol. So it's a 3 degree alcohol. You can also call it as tertiary alcohol. I hope, my dear friends, you are understanding. So normal alcohol can be 1 degree alcohol when OH group is present on 1 degree carbon, and it can be also 2 degree alcohol when OH group is present on 2 degree carbon, and it can be the tertiary alcohol when OH group is present on 3 degree carbon, my dear friends. I hope you have understood. Let us go for now allylic alcohol. In case of allylic alcohol, my dear friends, here also we can have 1 degree, 2 degree, and 3 degree alcohols here. So have a look here. If we talk about, my dear friends, this structure, CH2 double bond, CH single bond, CH2, OH. Now look here, OH is present on 1 degree carbon because this carbon is attached to only one carbon here directly attached to only one carbon. So it's 1 degree. So I will call it as 1 degree or primary allylic alcohol. 1 degree allylic alcohol. And you can also call it as primary allylic alcohol. Primary allylic alcohol. So let us go for now secondary. In case of secondary, my dear friends, the OH group should be present on secondary carbon, 2 degree carbon. So have a look here. If we take on the second example here, it will be like this. CH2, CH, then you have C, CH3, H, and OH. Now OH basically is present on sp3 carbon here, and this carbon is attached to 2 other carbon directly, one this and one this one. So direct attachment with 1 and 2 carbons. So this is a 2 degree carbon. So OH group is present on 2 degree carbon. We can call it as 2 degree allylic alcohol. 2-degree allylic alcohol. You can also call it as secondary alcohol. So secondary alcohol you can also call it as. Now let us look at now the tertiary allylic alcohol or 3-degree allylic alcohol. That will be CH2, CH, single bond C, CH3, CH3 and OH. Now you can yourself understand that this guy is our 3-degree allylic alcohol because it's attached, OH group is attached to the 3-degree carbon, because 3-degree carbon is attached to 3 other carbon directly. Have a look here. It's attached to 1, 2 and 3 carbons directly. So it's a 3-degree carbon. OH group is present on 3-degree carbon. So we call it as 3-degree allylic alcohol here. You can also call it as tertiary, TRT, that's enough, tertiary alcohol, tertiary allylic alcohol. So my dear friends, you have understood about allylic alcohols also. Let's go further and understand about benzylic alcohol. So I will draw the 3 structures and you can easily tell me that what kind of alcohols they are. They can be 1 degree, 2 degree and 3 degree, my dear friends. So first of all, I will draw one structure like this. So CH2OH. Now look here, OH is attached to the 1 degree carbon because it's attached to only one other carbon directly. It's attached to the carbon of benzene, but only one carbon is attached directly. So it's 1 degree. So obviously, if you take this example now, you have here C, CH3, H and OH. Here the OH group is attached to 2 degree carbon, my dear friends. And here finally we have here CH3, CH3 and OH. Here OH group is attached to 3 degree carbon, my dear friends. So obviously you can easily tell what are those. Here the OH group is attached to 1 degree carbon because it's attached to only one carbon directly. This carbon is 2 degree because it's attached to one carbon of benzene and one carbon of CH3. Yes. And this guy is attached to 3 carbons, CH3, CH3 and one carbon of benzene. So it's a 3 degree carbon. So OH group on 3 degree carbon is 3 degree alcohol. This is 2 degree alcohol and this is 1 degree alcohol. And this 1 degree alcohol will be called as 1 degree benzylic alcohol. 1 degree benzylic alcohol. And this one will be your 2 degree benzylic alcohol. 2 degree means secondary. And 3 degree means tertiary. So this guy is your 3 degree benzylic alcohol. That is tertiary benzylic alcohol. So I hope, my dear friends, you have understood this thing. Okay. So dear friends, we have learned about tertiary benzylic alcohol, secondary benzylic alcohol and primary benzylic alcohol. So dear friends, if we go back to our slide, you will find out we have classified the alcohols, okay, based on the attachment of OH group with sp3 hybridized carbon into 3 types: normal alcohol, allylic alcohol and benzylic alcohol. And further we have classified them into primary, secondary and tertiary. Here also primary allylic alcohol, secondary allylic alcohol, tertiary allylic alcohol. Here primary benzylic alcohol, secondary benzylic alcohol and tertiary benzylic alcohol, my dear friends. I hope you have understood this thing as well. Dear students, let's look into the common naming and IUPAC naming of alcohols. First of all, I must tell you that what is basically the common name of alcohols. Have a look. The common name of alcohols is alkyl alcohol. This is the common name. And when you look at the IUPAC name, it will be alkenol. So remember these two terms. Alkyl alcohol is the common name and alkenol is basically the IUPAC name of alcohols. So let's take on few examples to clarify it. Have a look here. CH3, CH2, OH. Okay. My dear friends, its common name has to be alkyl alcohol. Alkyl alcohol has to be the common name. And its IUPAC name has to be alkenol. Okay. So let us start doing it. Have a look here, my dear friends. Here you have CH3, CH2. That is your ethyl. and OH group is called as alcohol. So it's ethyl alcohol. So this becomes our common name. This is the common name. And when we look at alkenol, we will have here 2 carbons here. So 2 carbons will be called as eth, and single bonds are between carbon and carbon. So and OH group is called as all. So this ethanol is your alkenol, and it is the IUPAC name. So my dear friends, I hope you have understood how to write down the common name and IUPAC name. Let's take on few more examples to understand it better. Now, if we take an example of a straight chain of 3 carbon atoms. So when you have a straight chain of 3 carbon atoms, you must remember we use a term prefix N. N stands for normal. N stands for normal. And normal means the linear carbon chain, or you can also tell linear chain, my dear friends. So N stands for linear chain. So let me write it once again here. So N stands for linear carbon chain. And total number of carbons are here 3. So I will call it as propyl. So N-propyl, and OH group is known as alcohol. So this will become alkyl alcohol, and it's a common name. When you look at IUPAC name, it will be 1, 2, 3. So I can call it as prop and 1-all. So prop and 1-all will be the IUPAC name, alkenol. Yes. So let's take few more examples, my dear friends. Have a look here. CH3, CH, CH3, OH. Be careful here. Always understand when you have 2 CH3 groups, okay, in a particular compound, then you have to use the iso term for that. This side you have CH3 group, and this side also you have CH3 group. So remember, for 2 CH3 groups, you have to use the word iso. Yes, and total number of carbons are 1, 2, and 3. So I will use propyl. So isopropyl, and OH group is known as alcohol. So it's an isopropyl alcohol. But when we look at its IUPAC nomenclature, it's 1, 2, and 3. So it will become prop and 2-all, because on second carbon we have OH group. So it's prop and 2-all, my dear friends. So remember, iso is used when you have 2 similar alkyl groups, CH3 and CH3. So remember, it's only used for 2 similar alkyl groups when you have in a particular compound. So let's go further. If you understand one more molecule here, my dear friends, have a look. CH3, CH2, 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 and OH. And you know that it's a linear chain. Linear chain means normal chain. N stands for normal. Normal means linear. So I can call it as N-butyl because 4 carbons are there. So N-butyl alcohol. And the IUPAC name will be butanol. Butanol will be the IUPAC name. So let's take one more example. If you look here, my dear friends, CH3, CH, OH, CH2, OH. In place of OH, I want to write down the CH3 group, my dear friends. So let me remove this thing and put on CH3 group. So let's put a CH3 group here. Now one side we have an ethyl group and one side we have a methyl group. So we need 2 similar alkyl groups. But my dear friends, we don't have 2 similar alkyl groups here. So you cannot use the word iso here. Iso will be used only when you have 2 similar alkyl groups. But here one side we have ethyl, one side we have methyl. So iso cannot be used here. So what we are going to use here, have a look. First of all, we should understand that which carbon is this. This carbon is attached to 1 carbon on the right side and 1 carbon on the left side directly. So it's a 2-degree carbon. So when it's a 2-degree carbon, it's a secondary carbon. So I will call it as SEC. SEC means secondary. Secondary means 2 degree. 2 degree stands for secondary carbon. So total number of carbons are here 4. So I can call it as secondary butyl alcohol. And now if we start numbering this particular compound, we have to number it from this side, my dear friends, from the left side, because from left side, OH group is very, very near. OH group is very near from the left side. So 1, it will be 2, 3, and 4. So we will have here but and 2-ol. So but and 2-ol will be its IUPAC nomenclature, my dear friends. So let us go further and understand few more examples right out here. Have a look here. CH3, 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 and then you have OH. Now, my dear friends, here in this case, you have 1, 2, and 3 CH3 groups. Iso is used only for when you have 2 CH3 groups. But here we are having 3 CH3 groups. So here also we can't use the word iso because 3 CH3 groups are here. So dear friends, then what we are going to do with this problem, have a look. We know that which kind of carbon is this to which OH group is attached. We know that this carbon is basically a 3-degree carbon. Once again, I will draw this thing. OH group is attached to a 3-degree carbon. So obviously, when it's a 3-degree carbon, what we are going to use for it? We will be using the term 3-degree, or 3-degree is also called as tertiary. Tert we can use. So obviously, the total number of carbons are 4. So it will become tert. Tert means basically a tertiary. And total carbons are basically 4. So we'll get as tertiary butyl alcohol. And what will be the IUPAC naming? IUPAC naming will be 1, 2, and 3. Let us do the numbering like this, and this CH3 will become the substituent, my dear friends. So you will be having the IUPAC name as 2-methyl. Then you have 3 carbons which are numbered. 1, 2, 3 carbons are numbered here. Yes. So we have prop. Single bonds are there. So N. And on second carbon, we have OH group. So it is propan 2-ol. So 2-methyl propan 2-ol will be basically the IUPAC nomenclature of this particular compound. So let us go further, my dear friends, and understand one more example here. Have a look here. CH3, CH, CH3, CH2OH. And here again, you will find out that you have 2 CH3 groups here. When you have 2 CH3 groups, understand you have to use the word iso. Yes. And total number of carbons are 4. So it will become isobutyl alcohol. And IUPAC naming will be like this. Numbering should start from the side of functional group. So where from the functional group is closed, you have to start numbering from there. 1, 2, and 3. So on second carbon, you will have a methyl group. So it will become 2-methyl. Total carbons are 3. So propan 1-ol. Propan 1-ol. So my dear friends, you have understood this thing. So let's go further. Let's take on now alicyclic examples, 1 or 2. If you look at this cyclic structure and you put on OH group here, my dear friends, its common name will be cyclo. And obviously, we know that it's a hexane, but hexane will become hexyl because I need alkyl alcohol. So it will become cyclohexyl alcohol. So this will be the common name of this molecule. Common name is cyclohexyl alcohol. What will be the IUPAC name? IUPAC name will be cyclohexanol. Hexanol means alkanol, and hexyl alcohol means alkyl alcohol. So common name, and this guy is your IUPAC name of this molecule. So now let us go further and understand one more example. Have a look here. You have basically a molecule here with OH group, and then you have here CH3 group. And remember, this position with respect to the first position, this position is called as alpha position. Okay. So I will call it as, in common terminology, I will call it as alpha methyl. And then this ring and OH group will become cyclohexyl alcohol. Alpha methyl cyclohexyl alcohol will be the common name of this molecule. Common name. This is the common name. Now, if we look at the IUPAC name of this molecule, same molecule, so obviously we have OH group here and we have here CH3 group here. So this is number 1 and this is number 2 carbon. So it will become 2-methyl cyclohexanol. 2-methyl cyclohexanol. That will be the IUPAC name of this particular compound. So I hope, my dear friends, you have understood the common name and the IUPAC name of the alcohols. Yes. So you can practice more and more problems so that you will do little masters into this particular thing.
Dear students, let us understand the preparation of alcohols. There are various methods by which you can prepare alcohols. The first one here we have is from alkenes. Second one, hydroboration oxidation. Third one, oxymercuration, demercuration. From carbonyl compounds, from Grignard's reagent. So let's look into the first one, that how can we prepare alcohols from alkenes, my dear friends. Let's take on the first one. Have a look here. Preparation of alcohols from alkenes by acid catalyzed hydration. Hydration stands for addition of water. So you are going to add water to an alkene in presence of an acid, and that acid will act as a catalyst. So have a look here. Take on alkene, add water to it in presence of an acid, and that acid is basically your catalyst, and you will be getting an alcohol. So this is all about the reaction where the water is added to an alkene in presence of an acid to get an alcohol. But remember, this water should be added as per as Markovnikov's rule. So you have to add water here as per Markovnikov's rule, my dear friends. So let us understand it in detail. Have a look here. Let me take on one alkene here, CH3, CH, double bond, CH2. So dear friends, in this molecule, the reaction center is basically your carbon 1 and carbon 2. These are your reaction centers. And here you have to break the pi bond in this alkene. And remember, this third carbon will not take part in the reaction. So dear friends, have a look. I am going to add water to this particular molecule. And remember, this addition of water has to be done in presence of an acid. So I am taking sulfuric acid. And remember, this is acid catalyzed hydration of alkene, and I will be getting an alcohol, my dear friends. So I took an alkene, I'm going to add the water in presence of an acid, but how we have to add the water, that is the important point. We have to do here Markovnikov's addition of water. So here will be our Markovnikov's addition. So what is Markovnikov's addition, my dear friend? We have to add water as per Markovnikov's rule. So it's a very simple thing, my dear friends. In Markovnikov's rule, we have to first of all find out that which carbon in alkene contains less number of hydrogens, my dear friends. So this is our alkene and it is propene. This alkene is propene. And if you look at this carbon, my dear friends, it contains less number of hydrogen atoms, carbon number 2. We have here only one hydrogen. Only one hydrogen is here. And if you look at carbon number first, you will be having here 2 hydrogen atoms. When we talk of Markovnikov's rule, my dear friends, you should remember that OH group will attack that carbon which has less number of hydrogens. So OH group will go to that carbon which has less number of hydrogens. So it will attack the carbon number 2. So it will attack the carbon number 2. Correct? And then obviously the H will go to the carbon number 1. And this pi bond you have to break. So break the pi bond. Okay. Now, my dear friends, what is the product here? We'll be having here CH3, CH, You have broken the pi bond, so right here single bond, and CH2 and H will become CH3, and finally you have here OH group. So OH has gone to that carbon which has less number of hydrogen atoms. So obviously we will have here 1, 2, and 3. We are getting here prop and 2-ol, my dear friends. So that is the product, and that is Markovnikov's addition. And this is our acid catalyzed hydration, because it takes place in presence of an acid which is a catalyst. So let us take one more example, my dear friends. Have a look. CH3, C, CH3, double bond, CH2. Dear friends, this is our alkene, and obviously we have to break this pi bond. We have to break the pi bond, and you should first of all see that which carbon out of these two carbons containing double bond has less number of hydrogen atoms. And obviously if we look here, how many hydrogen atoms are here? 0. Here we have 0 hydrogen atoms. And here, how many hydrogen atoms are here? We have 2 hydrogen atoms here. So obviously this carbon, the central carbon, contains less number of hydrogen atoms, that is 0. So if we go for the Markovnikov's addition, my dear friends, so let's number it. 1, this is 2, this is 3. This will not take part in reaction. This will not take part in reaction. Only carbon first and carbon second you have to think of. So let us add the water to this, my dear friends. And in presence of an acid, H2SO4, and what will happen? Markovnikov's addition will happen. Markovnikov's addition. In Markovnikov's addition, you should remember, my dear friends, OH group will go to that carbon which has less number of hydrogen atoms. So OH group will go to that carbon which has less number of hydrogen atoms. So it will go here, because here we have 0 hydrogens. That means on this carbon we have the least number of hydrogen atoms, second carbon. And obviously the hydrogen will go to the first carbon. And you have to break this pi bond. This pi bond should be broken. So once you break the pi bond, have a look here. You will get here CH3C, CH3. Okay. Then this CH2 on addition of hydrogen will become CH3 here, and OH group will come here. So we have here 1, 2, and 3. So it will become here substituent. So we have 2-methyl prop and 2-ol. So that is our compound. I hope, my dear friends, you have understood that how to add water to an alkene in presence of an acid, okay, as per Markovnikov's addition, and you will be getting an alcohol. Okay, so you can take any example, even if you take example of a symmetrical alkene also, but there is no need to follow the Markovnikov's addition, because in symmetrical alkene you will be having carbon atoms with equal number of hydrogen atoms. So you can add hydrogen and OH anywhere, wherever you need. And this alkene, what I have taken right now here, is your unsymmetrical alkene. It's your unsymmetrical alkene. Okay, and the name of this alkene will be 2-methyl propene. It is your 2-methyl propene. 2-methyl propene. So unsymmetrical alkene we have taken, and we have added the water to it as per as Markovnikov's addition in presence of an acid which is acting as a catalyst, and we got 2-methyl prop and 2-ol, my dear friends. Dear students, you have learned the preparation of alcohols from alkenes by acid catalyzed hydration, and you have followed the Markovnikov's rule when you were adding the water to an alkene. But remember one important factor here. If carbocation rearrangement is possible in acid catalyzed hydration of alkenes then do not follow Markovnikov's addition. Do not follow Markovnikov's rule. So dear friends, if carbocation rearrangement is possible, at that time in acid catalyzed hydration of alkenes, we need not to follow the Markovnikov's rule. So please remember this important information. Now follow this sequence instead. So follow the given sequence. And what is that sequence? Have a look. This sequence you have to follow. H plus, then after that carbocation rearrangement. Just a minute. Carbocation rearrangement and followed by OH minus. So carbocation rearrangement followed by OH minus. So dear friends, you have to follow this sequence. Okay. And let's go further and understand few more points. Have a look here. Order of stability of carbocations. Remember always 3 degree carbocation is more stable than 2 degree, 2 degree is more stable than 1 degree carbocation. Now you will be thinking that why carbocation rearrangement takes place. Okay. Remember, carbocation rearrangement takes place for stability reasons. Remember always, if possible, let us suppose your 1 degree carbocation will try to change itself into 2 degree carbocation, or if possible, the 2 degree will change itself into 3 degree carbocation. So there is a term called as if possible. Then carbocation rearrangement will take place because 3 degree carbocation is your more stable. This is highly stable or more stable. And this is least stable. So dear friends, if you have a primary carbocation, it will try to change itself into secondary carbocation, and secondary carbocation will change itself into tertiary if possible. Then you have to do not follow the Markovnikov's rule at that time. Follow this particular sequence. H plus, then carbocation rearrangement, then after that OH minus. So this pattern you have to follow at that time. So let us go for it. Let's take on one example here. CH3, CH, double bond, CH2. So this is the molecule right out here. First of all, I will add H plus here, because at the end of the day in acid catalyzed hydration, we are adding H plus and OH minus. So first of all, I will shift this pi bond here, plus and minus. Then this will go right out here. And I'll be getting here CH3, CH plus, and here CH3. Okay. So dear friends, I'm not discussing any mechanism here. I'm just showing you a simple trick how to remember this particular thing. Okay. Have a look now here. This is a 2 degree carbon here. So we are getting 2 degree carbocation. So first of all, we have to see that rearrangement is possible or not possible. On right side, you have a 1 degree carbon, and here also 1 degree carbon. So obviously there is nothing like 3 degree carbon. If there is a 3 degree carbon adjacent to the 2 degree carbon, then rearrangement will happen. But in this molecule, we have only 1 degree and 1 degree carbon adjacent to the 2 degree carbon. So obviously rearrangement not possible. So rearrangement of carbocation not possible. So when rearrangement is not possible, obviously it will follow the Markovnikov's rule. It follows Markovnikov's rule. So what is that? In first step, you have added H plus. Now in second step, you will be adding OH minus, because total you have to add water. H plus and OH minus is water. That is hydration you have to do. So obviously now this guy will come right out here on the second carbon. And finally, you will be having here CH3, CHOH, and CH3. 1, 2, and 3. So this is my prop and 2 all. So in this acid catalyzed, you know what? This is your acid catalyzed hydration. Okay. In this acid catalyzed hydration of alkene, it has followed the Markovnikov's rule, my dear friends. You have seen that rearrangement is not possible. So when rearrangement was not possible, so it follows Markovnikov's rule. So wherever you feel that rearrangement is not possible, then directly follow the Markovnikov's rule. But there are some examples which I want to show you that where carbocation rearrangement takes place. Have a look here. CH3, C, CH3, H, C, CH double bond, CH2. So this is just one example. Have a look here. First of all, my dear friends, let us shift this pi bond. And I told you what is the trick. Then bring H plus and shift it here to CH2 minus. So you will be getting here CH3, C, CH3, then CH plus, and then CH3. So my dear friends, the carbon which you have gotten right out there is basically the 2-degree carbon. So we have here 2-degree carbocation. And remember this 2-degree carbocation and see the neighboring atoms. Here the neighboring atom is 1 degree and here it is 3 degree. That means here the neighbor is 3 degree. So when the neighbor is 3 degree, it has a hydrogen right out here. So that means 2 degree has a chance to change into 3 degree because its neighbor is 3 degree carbon. So how it will change into 3 degree carbocation now? Okay. So I will write down now here, this is less stable. So when it's less stable, it has a chance to change into 3 degree. So try to understand. Have a look here. Let me shift this bond between 3 degree carbon and hydrogen towards hydrogen. So this 3 degree carbon will get a positive charge and this hydrogen will get a negative charge. And this negative hydrogen is basically your hydride. Then this hydride will attack the CH plus, that is secondary carbocation, it will attack. So this shifting of H minus from 3 degree carbon, yes, is known as here towards 2 degree carbon is known as H minus shift, or we call it as hydride shift. So H minus shift or hydride shift. So in this case, carbocation rearrangement takes place. Carbocation rearrangement. This is the carbocation rearrangement. In this process, what happens? 2 degree carbon will change into 3 degree carbon. Have a look here now. CH3C, CH3. Now this carbon will get a positive charge and this will become CH2 and CH3. Now, dear friends, you have with you now 3 degree carbocation. So we have a 3 degree carbocation. So let's mention this positive charge here, 3 degree carbocation. And this is more stable. So for stability reasons, this rearrangement is taking place. Through hydride shift, it has happened. And finally, I told you the pattern was H plus carbocation rearrangement and then OH minus. So finally, OH minus will be here. OH minus will come and attack this tertiary carbocation. Okay, now this is tertiary carbocation. And finally, your product will be here. CH3, CH3. Then you have CH2 and CH3. And you will be getting here OH. So it will be 1, 2, 3, 4. So you have a substituent here at second carbon. So it will become 2-methyl butane 2-all. So that is the name of this particular compound. So in this entire process, you have learned certain things, my dear friends. Let me summarize. In first case, you have added H plus.
In second case, you have done carbocation rearrangement. And in third case, you have added now OH minus. So you have not followed the Markovnikov's rule here. Here, my dear friends, you have followed the sequence like H plus, carbocation rearrangement, and OH minus finally. So here the Markovnikov's rule is not followed. Please remember, when the carbocation rearrangement is possible. So here the carbocation rearrangement was possible. So no need to follow the Markovnikov's rule here. I hope everybody has understood. And remember always, carbocation rearrangement can take place through the following. What are those three things? Have a look. Carbocation rearrangement can take place through hydride shift, H minus shift, or it can take place through methyl shift, CH3 minus shift, CH3 minus shift, or it can take place through ring opening. The cyclic ring will open up, and in that way, the carbocation rearrangement can take place. So these are the ways by which carbocation rearrangement can take place, my dear friends. Okay, so please make note of this and practice more and more these kind of problems.
Dear students, let us understand now the second method of preparation of alcohols by hydroboration oxidation reaction. So we can represent it as HBO, hydroboration oxidation. Here, my dear friends, you have to add the water, but it will be as per Markovnikov's rule. So addition of water to alkene as per Markovnikov's rule, my dear friends. So you will be taking an alkene and you will be adding here water to an alkene, and this reaction is your hydroboration oxidation reaction, and obviously you will be getting an alcohol. And here you have to follow the addition of water should be done as per as anti-Markovnikov's addition, okay, or as per as anti-Markovnikov's rule. And the reagents which you require in the hydroboration oxidation will be, first of all, you have to use in one step, you will be using diborane B2H6 in THF tetrahydrofuran, and in second step you will be using hydrogen peroxide in aqueous NaOH. So dear friends, this is a two-step reaction. In one step you are using diborane, in second step you are using peroxide. But in both the steps, what you are doing hydroboration oxidation, and in hydroboration oxidation you are basically adding the water to an alkene, and finally you are getting an alcohol. So my dear friends, you need to remember only one thing here, that is, in hydroboration oxidation reaction we are adding water to an alkene and we are getting alcohol, but the addition of water will happen here in terms of anti-Markovnikov's rule. That is the only thing. So let us go for this particular reaction. Let's take an alkene, my dear friends, CH3, CH, double bond, CH2. So we are going to do the hydroboration oxidation reaction here. So in hydroboration oxidation reaction, my dear friends, we have two steps. In step number one, we will be adding diborane in THF tetrahydrofuran, and second step we will be adding here hydrogen peroxide along with aqueous NaOH, my dear friends. So these are our two steps right out here, and you should remember, my dear friends, in these two steps what should we do? We are basically adding the water to an alkene. So here we have to do addition of water. In these two steps, finally, we come to the conclusion that we are doing addition of water to alkene as per anti-Markovnikov's rule. Anti-Markovnikov's rule.
So what is the meaning of anti-Markovnikov's rule here? The OH will go to that carbon which has more number of hydrogen atoms. So my dear friends, let's have a look. Let's take our alkene here. We have the carbon number 1 here, carbon number 2 and carbon number 3. The 3 is not going to participate. Look here, we have here only one hydrogen. And here we have, in this case, 2 hydrogen. When we talk of the anti-Markovnikov's addition of water, my dear friends, when we talk of anti-Markovnikov's addition of water, you must understand here, my dear friends. Try to understand. Let's take one water molecule here. Because in these 2 steps, water is only added. So overall, in these 2 steps of hydroboration oxidation, this is our HBO. HBO stands for hydroboration oxidation. You have to add water. But water has to be added in terms of anti-Markovnikov's rule. So OH will go to that particular carbon which has more number of hydrogen. So OH will attack this first carbon here. And the H will definitely go to the second carbon. And first of all, you need to break this pi bond. So let us break the pi bond. So let us break the pi bond here. So you are breaking the pi bond. So dear friends, what is our product here? CH3, CH. And now CH will accept one hydrogen here. So it will become CH2. And then we have CH2 and the first carbon is getting OH group now. So we will be getting here OH. So we got here prop and 1-ol. So finally we got here prop and 1-ol. So this was all about the hydroboration oxidation. It's a 2-step reaction. And in those 2 steps, what we do, we are actually adding the water to an alkene. Okay. And my alkene here was unsymmetrical alkene, that is propene. And here we are adding the water to an alkene through the anti-Markovnikov's rule. Okay. And we are getting our product as here prop and 1-ol. Now you can take one more example as well. Let's take on CH3C, CH3, double bond, CH2. So dear friends, again, you are using the hydroboration oxidation you are doing. It's a 2-step reaction. So add diborane along with THF, tetrahydrofuran. In second step, you are adding the peroxide here. Okay, in a basic medium, that is NaOH aqueous. So in these 2 steps, what is happening, you should remember, my dear friends. As a trick, you should remember that you have to add water. So here we have to add water. Add water as per Markovnikov's rule or anti-Markovnikov's rule, as per anti-Markovnikov's rule. So dear friends, you will be adding water in these 2 steps. I am telling you overall what is happening in this reaction. So you have to add water. So when you are adding water, the hydrogen will go to that carbon which has less number of hydrogen. And the OH group will go to that carbon which has more number of hydrogen. And we know that this will not participate, this will not participate. Carbon number 1, carbon number 2, carbon number 3. So now, as far as anti-Markovnikov's rule is concerned, OH will go to that carbon which has more number of hydrogen. This carbon has here 2 hydrogen. And this carbon has 0 hydrogen, my dear friends. 0 hydrogen. So that means OH will go to that carbon which has more number of hydrogen, which is first carbon. And H will go to the second carbon. And break the pi bond. So you are going to break the pi bond. And my dear friends, overall, we are doing addition of water, but as per as anti-Markovnikov's rule. So finally, CH3, and here we will have CH2OH, and here we will get H. Yes, my dear friends. So, my dear friends, you have understood that how we are adding the water in hydroboration oxidation reaction. So this is our HBO, hydroboration oxidation reaction. And the compound which is formed here is 1, 2, 3. That is 2-methyl prop and 1-ol. So that is our product. So remember always, my dear friends, in hydroboration oxidation, it's a 2-step reaction. And in those 2 steps, you will be adding water actually to the alkene. When you are adding water to the alkene, and that addition of water should happen as per anti-Markovnikov's rule. That OH should go to that carbon which has more number of hydrogen, and hydrogen should go to that carbon which has less number of hydrogen atoms. So I hope, my dear friends, you have understood. And we have taken here obviously an unsymmetrical alkene. That is this is your unsymmetrical alkene. So please remember this particular thing. It is a very easy way to understand what is happening in the hydroboration oxidation reaction. Dear students, let us understand one more method of preparation of alcohols by oxymercuration demercuration reaction. What is basically this oxymercuration and demercuration reaction? Have a look. Here also we are adding the water to an alkene by Markovnikov's rule. So we have to follow the Markovnikov's rule here and add water to an alkene. So let's take on an alkene here, my dear friends. And we will be adding water to an alkene. And the reaction name is oxymercuration and demercuration. Let's write down OMDM. So we are doing here oxymercuration and demercuration. Here also we are adding water to an alkene, and as per Markovnikov's addition. So we have to do here Markovnikov's addition. That's it. So this is the Markovnikov's addition of water to an alkene, and finally your product will be alcohol. So dear friends, what are the reagents required in this process are mercuric acetate in first step in THF and water, and second step sodium boron hydride in basic medium, my dear friends. So let us understand it in detail, but you remember that we are doing also here addition of water, okay, and as per as Markovnikov's addition, and we will be finally getting an alcohol. So let us understand it in detail, my dear friends. Let's take on one alkene, CH3CH, double bond CH2, my dear friends. So this is our alkene, and what you are going to do actually, addition of water. But addition of water happens here in two steps. In first step, basically, you will be taking on mercuric acetate, and mercuric acetate is written like this, okay? So in THF and water. So then in second step, you will be using sodium boron hydride in NaOH. So this is a two-step reaction. In this two-step reaction, you have an alkene with you, which is propene. You will be basically adding water to this. So overall, you should remember here what happens. Markovnikov's addition of water. Addition of water. So when you know that there is a Markovnikov's addition of water, and remember, if these two steps will be named as oxymercuration and demercuration process. So now we have to add water as per as Markovnikov's rule. So take one water molecule and add it across carbon-carbon double bond. So carbon number 1, carbon number 2, carbon number 3, 3 is not participating. So now look here, the OH group will go to that carbon which has less number of hydrogen. So this guy will have less number of hydrogen. So OH group will go here, will attack here. And the hydrogen as usual will go to the carbon with more number of hydrogen atoms. And let us break the pi bond. So this is Markovnikov's addition. So OH group is going to that carbon which has less number of hydrogen, because this guy has only one hydrogen here. And this guy has more number of hydrogen, 2 hydrogens are here. So let us break the pi bond. Let's break the pi bond. So have a look here. CH3 we will get, C, and we'll be having here OH now, and this will become now CH3. And now, my dear friends, at this particular point of time, we have now 1, 2, and 3. That is, my dear friends, prop and 2-ol. So we are getting here prop and 2-ol, my dear friends. So let's take one more example. CH3, C,
CH3 double bond CH2. This is our alkene. The name of this alkene is 2-methylpropene. 2-methylpropene. And let us do its oxymercuration, demercuration. When we do oxymercuration, demercuration, my dear friends, there are two steps. In first step, we will be using mercuric acetate. This is mercuric acetate in THF and water, tetrahydrofuran along with water. Then you will be using sodium boron hydride in basic medium. So it's a two-step reaction. And in these two steps, my dear friends, you have to remember, you will be doing addition of water, as I told you, addition of water as per Markovnikov's rule. Markovnikov's rule. So when you add water as per Markovnikov's rule, obviously just add a water molecule here. And OH group will go to that carbon which has less number of hydrogens. This carbon number second, will have less number of hydrogens, 0. So obviously the OH will go to the second carbon and H will go to the first carbon, and let us break the pi bond. So we'll be having here CH3, C, CH3, CH3 and OH. This is our 2-methylpropane 2-ol. 2-methylpropane 2-ol. So that is the basically oxymercuration, demercuration, my dear friends. Okay, so please make note of this. Dear students, let us understand now preparation of alcohols from carbonyl compounds, my dear friends. So how we are going to prepare, have a look. First of all, we will take aldehydes and ketones, which are our carbonyl compounds, and prepare alcohols from them. Then we will take carboxylic acids and esters and prepare alcohols from them. So first of all, we will focus on from aldehydes and ketones. So dear friends, what we require here, what are the reagents required in this process? You can use, my dear friends, hydrogen along with nickel. Nickel is basically a metal here. Or in place of nickel, you can use platinum or you can use palladium. So this is the reagent of ours. Or if you don't want to use this, you can use, my dear friends, sodium in ethanol. So this will be also helpful in reducing the aldehydes and ketones to alcohols. If you don't want to use sodium in ethanol, you can use lithium aluminium hydride. Okay, if you don't want to use this thing, you can use SBH, that is sodium boron hydride. So let me write down NaBH4. So sodium boron hydride. So these many reagents can be used to reduce the aldehydes and ketones into alcohols. So let us prepare the first thing here. Let us prepare the alcohols from aldehydes and ketones by a reduction process. Have a look here. Let's take our aldehyde, CH3, C double bond O and H. This is our aldehyde. Now, dear friends, we are reducing the aldehyde, okay? And obviously, it's our carbonyl compound. This aldehyde is our carbonyl compound. And this contains 2 carbons, so we can also call it as estaldehyde. Now, look here, my dear friends. What are the substances or reagents you can use here? Dear friends, you can use here, my dear friends, nickel along with H2. Or in place of nickel, you can use platinum or palladium. That is addition of hydrogen. In second case, if you don't want to use this thing, you can use sodium in ethanol, C2H5OH. If you don't want to use this thing, you can use lithium aluminium hydride. If you don't want to use this, you can use sodium boron hydride. So any one among them you can use, and your work is the reduction of, your work is basically you are doing reduction of, okay, aldehydes and ketones into alcohols, because all these substances are reducing agents. They will provide you hydrogen. All these substances are the source of hydrogen, my dear friends.
So they are your reducing agents. So these are your reducing agents, my dear friends. So I can call them as reducing agents. So when these reducing agents will reduce the aldehyde, my dear friends, what's going to happen here? You will be getting CH3 and aldehyde will be reduced to the alcohol. So you will be getting CH2OH. That means you are reducing the CHO group to CH2OH. So I am getting here ethanol, my dear friends. So dear friends, the aldehydes and ketones can be reduced to alcohols by using the reducing agents. So let us summarize it, my dear friends. Have a look here. If you have an aldehyde with you, or you may have a ketone with you, C double bond O and CH3. This is the target point. This is the target point. First one we have an aldehyde and second one we have a ketone. So now let us use the reducing agents. So you can use any reducing agent here. Let's use lithium aluminum hydride, or you can use sodium boron hydride. You can use sodium in ethanol. You can use nickel along with hydrogen gas. So obviously you can use anyone. I have already mentioned what are the things you can use. So anyone you can use. Sodium in ethanol you can use also, or you can use H2 along with the nickel or platinum or palladium. So in both the cases, reduction will happen. So obviously this is a reduction reaction. So reduction will happen and you will be getting here CH3, CHO will be converted into alcohol, CH2OH. So CHO is reduced to alcohol. In the same way, CO will be also reduced to alcohol, CHOH and CH3. But the only difference is that in case of aldehydes, my dear friends, in case of aldehydes, your aldehyde is converted into which alcohol? This is a 1 degree carbon, it's converted into primary alcohol. But when you look at the ketone, your ketone is converted into, look here, this is a 2 degree carbon, so it's a secondary alcohol. So aldehyde is giving you the primary alcohol and ketone is giving you the secondary alcohol. And these are all your reducing agents. Their work is to reduce the aldehyde and ketones into alcohols. Aldehyde will give you primary alcohol and ketone will give you the secondary alcohol, my dear friends. So let us go back. My dear friends, now we can prepare the alcohols from carboxylic acids and esters. And what are the reagents required here? Have a look. The reagent required here is lithium aluminum hydride for this process. So we are using a reducing agent here. It's a strong reducing agent. Remember, lithium aluminum hydride is a strong reducing agent. And it will reduce the carboxylic group and esters into alcohols. And remember one important point, sodium boron hydride does not reduce carboxylic acids and esters. This is the important point, my dear friends, you should remember. So let us prepare the alcohols from carboxylic acids and esters by a reduction process. So let us go for the reduction process, my dear friends. Have a look. Let me take on. So obviously, let's write down one statement. Okay. Let's write down one statement here. Just a minute. So we are just basically reducing reduction of carboxylic acids and esters into alcohols by using strong reducing agent like lithium aluminum hydride, okay, followed by acid hydrolysis. So followed by acid hydrolysis, my dear friends. Have a look here. So see here, the first step is we have to use lithium aluminum hydride, and then second step will be acid hydrolysis. So remember that important point. So let's go back. Let's take on our
carboxylic acid first. So if we take a carboxylic acid here, CH3, CH2, COOH, this guy has to be reduced. It has to be reduced to alcohol. And for its reduction, I will be using a strong reducing agent in first step, that is lithium aluminium hydride. And in second step, I will be doing the acid hydrolysis. So I will use H3O plus, or you can use H2O/H plus. So these are the two steps. And this carboxylic group has to be reduced to the alcohol. So I will be getting here COOH will change into CH2OH. So it's reduced to an alcohol, my dear friends. So your carboxylic acid is reduced to alcohol by using lithium aluminium hydride as strong reducing agent and followed by acid hydrolysis. So dear friends, remember that carboxylic acid can be also reduced to an alcohol, my dear friends. And now let us talk about whether this reaction will take place in presence of SBH or not, sodium boron hydride. So remember here, sodium boron hydride, NaBH4, you can make a note of this, okay, does not reduce because it's weak reducing agent. So we will say does not reduce carboxylic acid and esters. So if you write down a reaction here, let's suppose you have a carboxylic acid here, or you have an ester. Let's suppose ester you have. This is carboxylic acid and this is ester. This is our carboxylic acid. So if you use sodium boron hydride here, in this case also if you use sodium boron hydride, yes, so no reaction. Why? Because sodium boron hydride is a weak reducing agent. So it will not reduce carboxylic acids and esters. So let's come back to the lithium aluminium hydride. So let's talk about now here ester. C double bond O and OCH3. This guy is our ester. Okay. So this is our ester. Remember here, we will be doing two things here. We will be using first step lithium aluminium hydride and followed by acid hydrolysis. Correct? So what we are going to do, you break the ester into two parts. Break the ester into RCO group and CH3O group. That is acyl group. This is your acyl group. Break the ester into acyl group. And this group is called as alkoxy group. So you have broken the ester into two groups. Then you are using a strong reducing agent followed by the acid hydrolysis. So here in case of ester, you will get two alcohols. First of all, this acyl group will be converted into RCH2OH. And this alkoxy group will be converted into CH3OH. So now your two products are RCH2OH, that is from acyl group, and another one will be CH3OH. So two alcohols you are getting while doing the, reduction of esters. You are getting two alcohols, two types of alcohols, my dear friends. So let's take on one more reaction here. Have a look here. Let's suppose CH3, CH2, C double bond O, and then you have O, CH2 and CH3. You are knowing that this is your acyl group and this is your alkoxy group. So you will be getting two types of alcohols from ester. So let's use lithium aluminium hydride. Along after that, we'll do acid hydrolysis. So dear friends, the two products with you will be, the first one you will get CH3, CH2, and this CO group will change into CH2OH now. This is one alcohol, and another one will be alkoxy group. Alkoxy group will become CH3, CH2OH. So you are getting propanol and ethanol. So this is how you are going to reduce the carboxylic acids, esters, aldehydes, and ketones and convert them into alcohols. I hope everybody has understood this particular thing.
Dear students, let us see how to prepare alcohols from aldehydes and ketones by using Grignard's reagent followed by hydrolysis with water or dilute HCl. So let us take on aldehydes or ketones. So my dear friends, we have here R, C double bond O, then we have H here. If you replace H by CH3 group, it will become your ketone. So we are taking here, my dear friends, an aldehyde, or you can mention you are taking a ketone. So what we are going to do with this, try to understand. It's a two-step reaction. In first step, we'll be using Grignard's reagent, RMgX. Okay, so we are treating aldehyde or ketone with Grignard's reagent in one step. And second step, we will do the hydrolysis by using water, or you can use dilute HCl as well. You can use dilute HCl as well. So first of all, you must know that the Grignard's reagent, the first one, remember, this Grignard's reagent will be the source of R minus. So this guy, the Grignard's reagent which you have here, understand it is the source of R minus. So Grignard's reagent is a source of R minus. Let's go to the water now. Second step. So in second step, we have water. In place of water, you can also use dilute HCl. And let us see, the water is a source of which thing? So water will be the source of here H plus. So my dear friends, Grignard's reagent is the source of R minus, that is alkyl group, and water is the source of H plus. Now let us shift this bond here, my dear friends, the pi bond between carbon and oxygen of carbonyl group. Let us shift it. Once we shift it, we'll get a negative charge here and positive charge here. Now we have two things with us, R minus which comes from Grignard's reagent and H plus which comes from water. So R minus will surely attack the C plus of carbonyl group. So obviously the R minus will come down and it will attack the C plus here. And the another thing, H plus which comes from water will go and attack the O minus here. So my dear friends, our product will be R, C, O here, and then we have H and CH3. We know that R group is attacking, R minus is attacking the carbon of carbonyl group. So R minus is attacking the carbon of carbonyl group. So R will be here, my dear friends. And we know that H is attacking the O minus. So obviously H will be here. So we are getting an alcohol. So here we can get secondary alcohol from aldehyde and tertiary alcohol from ketone. In general, I will write down we are getting alcohol. So remember, Grignard's reagent will be the source of R minus and water is the source of H plus. So obviously, this is how the reaction takes place. Remember, this is just a trick to remember the reaction. Mechanism is something different. So by this trick, you can remember that where will R minus go and where will H plus go. So please remember this thing and let's take an example. CH3, C double bond O and H. This is acetaldehyde. This is acetaldehyde. So let us use in first step the Grignard's reagent and let us use CH3, okay, MgBr as our Grignard's reagent, followed by hydrolysis with water. So dear friends, now have a look here. Let us shift this sigma bond plus and minus. So this guy is a source of R minus, and that R minus is nothing but it is your CH3 minus. It's a source of CH3 minus. And now if you look at the water, my dear friends, this water is the source of H plus. Now you have to shift this pi bond from carbon to oxygen. So negative charge here and positive charge here. So my dear friends, now we will be taking the H plus and H plus will go and attack the O minus. And finally, we'll be taking CH3. It will go and attack the carbon and the product will be CH3, CO, and in H, O will receive H. And then you have H here. And this carbonyl carbon is receiving CH3 group. So my dear friends, this thing has come from outside. This thing has come from outside. CH3 has come from Grignard's reagent and H has come from the water. So my dear friends, remember this thing. And obviously the alcohol which is formed here is 2-degree alcohol, because the carbon in the center is 2-degree carbon. So we are getting 2-degree alcohol here, or you can also mention we are getting secondary alcohol here. So acetaldehyde or aldehydes will give you secondary alcohol when they are treated with Grignard's reagent followed by hydrolysis with water. Now let us take ketones as an example. So same pattern will happen there also. Same thing will happen also there. It also has a carbonyl group. First of all, you can shift the pi bond here. So show plus and minus. This is just for understanding, my dear friends, so that you will easily get to know that where will be the attack. Let's take on the Grignard's reagent here. CH3 MgBr, methyl magnesium bromide, followed by, you have to take water. So remember one thing only for your competitive exams, that is, have a look. This guy is a source of R minus, and that R minus is nothing but it will be CH3 minus. It's a source of CH3 minus, and water will be the source of H plus. Now you can adjust these things now. Okay, so H plus will go to the O minus right out here, and CH3 will go to the C plus of carbonyl group. And this substance which we are using here is acetone. It's a ketone. So obviously we'll be having here CH3, C, CH3. Then you have here OH, and finally we have here CH3. This CH3 has come from the Grignard's reagent, and this H has come from the water. So obviously this carbon which is in the middle is a 3-degree carbon, because it's attached to 3 other carbons directly. So here we are getting tertiary alcohol or 3-degree alcohol. You can also call it as tert alcohol, that is tertiary alcohol. So ketones are giving me the tertiary alcohol, but aldehydes are giving me the secondary alcohol. Let's take one important example here. Let us suppose if you have a carbon dioxide with you. Let's suppose you have a carbon dioxide with you, and I am treating the carbon dioxide with Grignard's reagent followed by hydrolysis. So I am treating carbon dioxide with Grignard's reagent. So R MgX followed by hydrolysis. And we know that this guy is a source of R minus. This guy is a source of R minus, and this guy is a source of H plus. Now let us shift one pi bond, my dear friends. Let's shift any one pi bond. Let me shift this pi bond. This will get negative charge. This will get positive charge. So R minus will come and attack here on this carbon, and H plus will go and attack here. So dear friends, you will be getting C, single bond O, and double bond O. So for this oxygen, my dear friends, okay, we will be writing here, hydrogen is going here, and the R minus goes here. So it is RCOOH. So that means you are getting carboxylic acid. So dear friends, when you are treating carbon dioxide, when you treat carbon dioxide with Grignard's reagent followed by the hydrolysis with water, you will be getting carboxylic acid. So remember this thing. So dear friends, I hope you have understood this trick. Have a look here. You should understand now that aldehydes will give you secondary alcohols, okay, and the ketones here will give you tertiary alcohols. But if you have you're using carbon dioxide will give you carboxylic acid. It will make carboxylic acid. So please remember this important information. I hope everybody has understood this thing, my dear friends.